Hello guys, welcome back to the channel. Today we are going to see one of the application of binary exponentiation, which is effective computation of Fibonacci numbers using matrix exponentiation. We will see some of the properties of Fibonacci numbers, what this Fibonacci series is, and where this series can be used, and how, and then the coding part of it. What is the formula for the Fibonacci numbers? How we can calculate the Fibonacci series in linear time, and how we can calculate the nth Fibonacci number in O of log n time. Okay, so first let's see what is the Fibonacci series. So we are using zero based indexing. So you have been given two numbers, zeroth number and first number, which is 0 and 1. So for the next number you have to add the previous two. For the second number you have to add one first number and second number, it is 1. For the third number you have to add second and first number, which is just 2. So now, as the series 153 plus 8, 8 plus 5, 13, 21, then 34, at a dash 4, 5, 6, 7, 8, and 9. So this series look like this. So what is the general equation for it? Is it fn equal to fn minus 1 plus f of n minus 2, and you are given f of 0 equal to 0 and f of 1 equal to 1. So it is the Fibonacci series. So the Fibonacci sequence defined as follows: f0 equal to 0, f1 equal to 1, and f of n equal to f of n minus 1 plus f of n minus 2. Okay, so the series look like this: 0, 1, 1, 2, 3. Any number is the sum of the previous two except the first zeroth and first number. So let's see some of the interesting properties of Fibonacci number. First is Cassini's identity. You can prove all these properties using mathematical induction. So first is Cassini's property, which states that if nth Fibonacci number, and you will take the multiplication of previous and the next Fibonacci number minus the current k square, it will come out to be minus 1 ki power n. So let's take an example from here itself. Let's take 6th Fibonacci number n equal to 6. Then f of 5 will be, f of 5 is 5, f of 7 is 13, minus f of 6 is 8, 8k square equal to 1. 65 minus 64 equal to 1, which is minus 1 ki power 6. Minus 1 ki power 6 is also 1, as you can see. These all properties you can prove using mathematical induction. Second is the addition rule. Addition rule states that f of n plus k equal to f of k, f of n plus 1 plus f of k minus 1 into fn. It is also another formula for calculating f nth Fibonacci number. For example, if we have to calculate f of 8, and you have, so 8 can be broken in many parts. So let's break it into 2 plus 6. So let's take this is n and this is k. So what the formula states that it is f of n plus 1 into f of k plus f of k minus 1 into f of n. So what is f of n here? F n plus 1, f of n plus 1, f of 3. F of 3, as you can see, f of 3 is 2. F of 3 is 2. What is f of 6? F of 6 is 8. F of 6 is 8. F of k minus 1, f of 5. F of 5 is 5, and f of 1 is 1 into 1. So it is 16 plus 5 equal to 21. And you can see that the 8th Fibonacci number is also 21. So it is another formula for calculating n Fibonacci number. So it is states like this: the addition rule. So by applying the previous identity k equal to n, we get this equation. If you replace k with n, it will become f of n into f of n plus 1 plus f of n minus 1 into fn. You will take fn common, then this equation will come out. So another identity, GCD identity, it states that GCD of two Fibonacci numbers equal to f of m comma f of n equal to f of GCD of the two numbers m comma n. So let's also see an example for it. For example, let's take m equal to 3 and n equal to not, Let's take m equal to 3 and n equal to 6. So what it states that GCD of f of 3 comma f of 6 equal to f of GCD of 3 comma 6. So what will the answer for this? F of 3 comma f of 6. F of 3 is 2 and f of 6 is f of 3 is 2. So GCD of 2 comma and f of 6 is 8. It will become 2. And what is the answer for this? So GCD of 3 comma 6 is 3. So f of 3 comma 6 GCD is 3. What is f of 3? F of 3 is indeed, as you can see. So it is another identity for the Fibonacci numbers. So these are some of the identities. You can Google it, and if you want to see the proving, then you can Google it or do the chat GPT or see its proving. These can be proved with mathematical induction. We are not going to prove here. So where this Fibonacci series can be used, it can be used in Fibonacci coding. We can use the sequence to encode positive integer into binary code words. According to Zeckendorf theorem, any natural number can be uniquely expressed as sum of Fibonacci numbers. So any number n, you can represent it using sum of the Fibonacci number. It can be represented as sum of some Fibonacci number. For example, 19. 19 can be represented as 13 plus 5 plus 1, which is f7, f5 plus f2. For example, let's take 1 minute. So I should shift it up. So let's take first write down the series 0, 1, 1, 2, 3, 5, 8, 13, 21, 34. So let's take 18. So how can it be represented as sum of Fibonacci numbers? 13 plus 5, 13 plus 5 is 18. So these two numbers, so by using these two numbers we can represent 18. So for 17, 17 can be represented as 13 plus 3 plus 1. So as you can see, any numbers, so like take 20. So 20 can be represented as 13 plus 13 plus 5 plus 2. 13 plus 5 plus 2. So as you can, so you can see any number n can be represented as sum of two Fibonacci, sum of some Fibonacci numbers. And interesting property is that the two number, that in it, in the, for example, you take some Fibonacci numbers, and interesting thing is that no two numbers will be consecutive in the Fibonacci series. It is the interesting thing. For example, in 20, 13 plus 5 plus 2, no numbers are consecutive. In 17, it is also 13 plus 3 plus 1. In 18, it is 13 plus 5. So no two numbers are consecutive. It is the property to note down. So for example, it follows that Fibonacci coding, and we can describe this representation with binary representation. If f of I plus 2 is used in the representation, the code will be appended by 1 to indicate the end of the code. Let's notice that this is the only occurrence where two consecutive 1 bits appear. When, because we will append 1 to the binary codes to mark the end. So let's take example this, how 19 can be represented as it. It is a simple greedy algorithm for this code. It states that iterate to the Fibonacci number from largest to the smallest unless you find 1 less than or equal to n. Suppose this number is f5, subtract f5 from n and put 1 in the I minus 2th position of the code word, and do this until there is no remainder, and add final 1 to the code word to indicate its end. So for example, for 19, what we will do, as 19 will be represented as 13 plus 5 plus 1. So it is 0, 1, 1, 2, 3, 5, 8, 13, 21 and 34. As 19 will be represented as F7, which is 13, F5, which is 5, and F1, which is it is 13 plus 5 plus 1. So what this algorithm says that we will iterate from the largest number to the smallest number. So first we will go from, let's say we start from this number 34. Is 19 smaller? Is 19 is greater than or equal to this? No. Is 19 is greater than or equal to this? No. Is 19 is greater than or equal to 13? Yes. So what we will do, we will subtract 13 from 19. 19 minus 13 equal to, we are left with 6, and we will append what is, which is this position, it is seventh position. So we will, so what, let's, it is the binary code this. So we will append in I minus 2th position, means fifth position we will append a 1. So 0 1 2, 0 1 2 3 4 5, we will append 1 here in the fifth position. So now we are left with 6. So will go from here. Is 6 is greater than? No. Is 6 is greater than 5? Yes. So we will minus 5. So 6 minus 5 equal to 1. We are left with 1. And which is this index? It is 5. So we will append on the third index 1. So we will append third index 1. Then we will go in this way, and 1 is greater than equal to 1. Yes. And so it is the second index. So in the, so it is second index. So in the zeroth index we will append 1, and I minus 2th index. 1 0 0 0, and at the end we have to append 1 to mark its end. So it is the binary code for 19th number using the Fibonacci coding. As you can see, 1001 011, 1001 011, and all these codes come like this only. Okay, so, and to get the number, the same algorithm will be, was to decode a word, first remove the final one, and then the, and as you know that it is the zeroth bit. For example, if you are given this code word, how will we decode that, which numbers code is this? So first we will remove this last one. Then for the, it is second, it is the zeroth number. So which number have been added here? So it will be I plus 2th number, f of I plus 2. It will be second number is added, so 2. So here it is on the third index, it is 1. So f2 plus f5 plus f7, it is indeed 1 plus 5 plus 13, so it is 19. So you can decode in this way. That is one of the use case of Fibonacci numbers, to decode a certain word, to encode a certain word, sorry. So formula for the nth Fibonacci number, the closed form expression, this is also known as the Binet formula, even though it is already known as mover. Fn equal to this 1 plus under root 5. This formula can be used to find the Fibonacci number. This formula is easy to prove by induction, but it can be deduced with the help of the concept of generating function or by solving a functional equation. You can immediately notice that the second term absolute value is 1, less than 1. It is always less than 1, and also decreases very rapidly. Hence, the value of the first term is almost Fn. So Fn equal to 1 plus under root 5 by 2 upon under root 5, this equation. So the square bracket denotes the rounding to the nearest integer. It is the formula for Fn. So it needs very high accuracy when working with fraction numbers. So there are little of use case in practical calculations. So we, so how we can find the nth Fibonacci number in linear time by using coding. So it is simple, as we have seen that the nth Fibonacci number can be calculated by using the previous two Fibonacci numbers. F of n equal to f of n f of n minus 1 plus f of n minus 2. So you will initialize two numbers. First is 0, that's equal to a is 0, b is 1. Then you will run a while loop. While, for example, you have to find the fifth number. So you will run a while loop or for loop. So and here what will be, you will temp equal to a plus b. Then the current number will be swapped. So a will become b. So a equal to b and b equal to temp. It is like this. You have these two numbers and you have find this number. It is temp. So this number was initially b and this number was initially a. So a will become b. So a equal to b and b will become temp. So b equal to temp. This is the equation, and at the last, what number will be at a nth number will be in the variable a. This is a simple approach for finding the Fibonacci number in linear time. In Fibonacci, it is a function int equal to 0, b equal to 1. For int I equal to 0, I less than n, I plus plus, int time equal to a plus b, b equal to time, return a. It is a simple function, and in this way you can obtain the nth Fibonacci number in O of n time. Okay, so it is the very easy thing. You can code it by yourself. So let's see how we can find the nth Fibonacci number in O of log n time. So it is easy to prove the following relation. It is the relation by which we can use the nth Fibonacci number in log n time. This matrix raised to power n equal to f of n plus 1 fn f of n fn minus 1. So how we can prove this equation? This equation can be easily proved using mathematical induction. So let's see how we can prove it. So to prove this equation, like for the Fibonacci number, let's start from the base case. If you put n equal to 1, sorry, n equal to 0, if we put n equal to 0, so it will be, so as it is, let's put n equal to 1, sorry. So a1 equal to 1 1 0 0 0, and if you raise to the power 1, the matrix is like this: f2 f1 f0. It is indeed true, because f2 equal to 1, f1 equal to 1, f1 is also 1, f0 equal to 0. Now assume that it is just the mathematical induction theorem, nothing else. Now assume that the statements hold for n equal to k, so it will be like this, and you want to prove that it holds for n equal to k plus 1. So what is a of k plus 1 equal to a of k dot a? So in this you have to multiply the two matrices. So yeah, in this you also need to know the matrix multiplication. We will use the matrix multiplication here. Let's say we have two matrices, this and this. So its first row is multiplied by its first column, and that will be the answer for this first cell. Its second row multiplied by first column, it will be the answer for this. For third row multiplied by its first column, it will be the answer for this cell. For first row multiplied by second column, it will the first row, and then it will the answer for this cell, means first row and second column. The multi So it is like this. For example, 2 1 3, and here it is, for example, 4 6 7. Any matrix like this. So 2 into 4, so how matrix multiplication is done? 2 into 4 plus 1 into 6 plus 3 into 7. So 4 to the 8, 8 plus 6 plus 21, 8 6 14 21 35. So answer for this cell will be 35. So in this way the matrix multiplication is done, and for all the cells you will find, and you will eventually get the answer matrix. So let's come back to its proven. So here we will multiply the matrix. So f of k plus 1, and it is the a is the original matrix f of this. k plus 1 plus f of k, because f of k plus 1 into 1 equal to f of k plus 1, f of k into f of 1 equal to f of k. So these two will be added, and so like this for this column it is f of k plus 1 into 1 plus f of k into 0, so it is f of k plus 1. For this f of k plus f of k minus 1, and for it is f of k. So now we need to show that it is equal to f of k plus 2 and this, and indeed as you can see f of k plus 1 plus f of k, as it can be stated as f of k plus 2, as f of k plus 2 is the sum of previous two Fibonacci numbers. This is this f of k plus 1, it is as it is f of k plus f of k minus 1, it is f of k plus 1 and f of k. So it uh, it gets proved using mathematical induction. So this formula is correct. So any matrix, so this matrix raised to the power n will give the nth Fibonacci number in this position. So, and it can be found in O of log n time using binary exponentiation. As in binary exponentiation, for example, a की power n can be calculated in log n. So here this a is represented by a matrix. So any matrix की power n means we have to raise this matrix, we have to multiply this matrix in power. What we will do, a into a up to n times, and here just it is like this, we have to multiply the matrix and nothing else. So in so like the binary exponentiation code, it was like this. We will do res equal to res into a and a equal to a into a, as we have seen. So here instead of this result it will be a matrix result, and here it will be the matrix itself. And so let's see its code. So here it is we have made an struct of matrix, and as you can see this matrix is a 2 by 2 matrix, so it is almost log n time only. So so we will take two matrix base, which is indeed this matrix, and to which power we have to raise it, so it is log n. So matrix answer, so initially we will declare the answer matrix as this 1001. It is the identity matrix, and while n, and while n is greater than equal to 0, so if n is odd, as we have seen in the previous video, if n is odd, here we have taken in, instead of n b, if b is odd, what we will do, res equal to res into a, and then equal to into a and b divided by 2. So the same thing is done here, answer equal to answer into base. We have taken the identity matrix, as here we have taken answer equal to 1. So base into base and divided by 2. So how will these matrices be multiplied? So here we have used the operator overloading thing, but we will see in the code. We will just be doing with 2D matrices, 2D vector. So here it is just the matrix multiplication code and nothing else. And we will find the nth Fibonacci number at the position this position 0 through and first column. So it is value of 0, 1. Let's say its code. It is the number of test cases, and for example we have to find eighth number. So what we will do, first we will take the input and see, and what we will do, we will declare the identity matrix vector or vector of answer, vector of answer of size 2, vector have seen answer of 0, 0 equal to 1, and answer of 1, 1 is also 1. As you can see here, it is the identity matrix. I have done the same thing here. So what will we do? While n is greater than equal to 0, n is greater than 0, if n is odd, if n mod 2 equal 1, so what we have to do? Answer. So first we have to make a multiply function, multiply answer matrix with the base matrix. Let's make another matrix base vector of and base matrix, one vector of int 2 and base matrices base of 0 0 equal to 0, base of 0 1 1, here it is 1, sorry, base of 1 0 equal to 1. In this position there is only 1, and vector row and base of 1 1 it will be 0. So here is the it is the base matrix. Sorry guys, my laptop was get off. So now let's resume where we are. Yeah, so we have we, we have made the identity, we have made the base matrix. So what we have to do, if n is odd, then we have to do answer equal to answer into base, else we have to multiply the base by itself. And so answer equal to make a function for multiplying the matrices, this, and this, else we have to else no, we have to multiply the base in every iteration. Base comma base, and we have to divide and divide by 2 and divide by 2. At the end we will output. So where so answer will be at the position, let's name variance, at the position of answer of 0 and 1. We will print the answer. So let's we can multiply function for it. Multiply vector of int and answer comma vector int and base. Okay, so we do answer equal to this. Make another vector C of size 2 comma size 2 0, in which we will store the answer. Multiply the function I int equal to 0 y less than 2 I plus plus or j less than n j plus plus or n equal to 0 k less than n k plus plus. What is so C of ij plus equal to k of ik into b of jk. Can see here net of I equal to ik into kj. Because it is we have to multiply the row with the entire column, and at the end what we have to do that. So let's return a vector from here. It's a vector and we return this vector C and make answer to this. Store the answer that matrix and store in the base this matrix. Let's run our code and let's see if there is any mistake. Multiply function. No match for operator. It base comma base. And then it is 2. We know that. Let's make it A and B, not answer and base. Matrix A multiplied by matrix B. No match for operator equal to ans equal to this. Make a vector of LC. No, here we have to put int. We are returning an int vector. Int. Here I use mostly long int. So I have this problem occurring. Let's see what answer will come. So the code is taking too long to getting execute. It is a whole code. They have just do the operator overloading thing here, and nothing else to use the multiply symbol for this. You can read it in the OOPS concept in C++. What is operator overloading? All stuff like this. And we have just made another function for doing the multiply thing. So it is 21, and you can see that what is 8th number in the series. Where what is 8th number in the series? It is indeed 21. And for example, let's take another number, 9th number. That is 34 as we know. Let's see it is coming 34 or not. It is taking too long to execute. Laptop is getting a bit slow. Let's count how many operations we are. How many operations this loop is getting. How many times this loop is getting executed. Let's find out that. So for example, for it is indeed 34. For example, let's find number 100. How many times the loop will get executed? For the number 100, laptop is getting a bit slow, very slow. It is indeed the 7 times, and it is coming negative due to overflow. So let's take another number, for example, some small number, let's say 60th number. we have just taken int. That's why it is getting overflow, because I think 100 number is a too large number. 100 5 number, 5 100 5 number is too large to get stored into data type. Let's see what is 60th Fibonacci number. 60th Fibonacci number is indeed also very large. Let's look at 40th Fibonacci number. It come in, yeah, 40th Fibonacci number can come in this 1820. 60th Fibonacci number is, that's 40th. 40th Fibonacci number is 1023341555. It is 1023341555, and the loop is executed only 6 times, and the log to 40 is approx 6, as 2 to the power 5 equal to 32 and 2 to the power 6 equal to 64. Okay, so this loop is executed only 6 times, as you can see. So its time complexity is of log n, and this multiply function is a bit constant function, as we are multiplying only 2 into 2 matrices. So it is, so as you can see, it will go approx for 8 times. 2 into 2 equal to 8. So it is just a constant number, so the time complexity is of log n for this matrix exponentiation thing for finding the Fibonacci number. In the matrix exponentiation, you need to have the knowledge of two things. First, matrix multiplication. Only the two things are used: matrix multiplication and the binary exponentiation. And by combining these two, we say that it is matrix exponentiation, because we exponentiate the matrix over here. And exponentiation is can be done by simple multiplying things. So it is the things. So there is another method known as for matrix expression, known as fast doubling method, for by expanding the above matrix f equal for n equal to 2 into k. So we put at the position of n 2 comma 2 into k. So it will become f of 2k plus 1. We have just put at the place of n 2k. So we have to exponentiate this matrix 2k times. So it will eventually will see that it is fk plus 1 fk minus 1k square. Okay. So by using these equations, you will get to know that f of 2k plus 1 is nothing but f of k plus 1k square plus f of k square, and f of 2k is this f of k into f of k plus 1 f of k minus 1. Okay, so by using these above two equations, you can write a simpler code. This is also the binary exponentiation code only, but you will get this, and you need not to have a 2 into 2 matrix. You can just have a pair and you can get the answer. The above code will return f of n and f of n plus 1 as a pair. This you can do a dry run by yourself. It is indeed just this equation only, and you will get the answer. We will see further topics in further videos. Thank you guys. If you have any doubt, you can you can write down the comment section, and I will give the link of this. I will give the link of this article in the description box. And if you want me to make a video on any another topic, you can ask freely in the comment section. Thank you guys and happy learning.